Let's do it now. Yes. Hello, everyone. Thank you for coming. We are going to start because we have like a very tight schedule. What is the reason? Yeah. Well, it's not clear. This is going. So because that time we had a problem. So yeah. I will try to introduce the speaker so it can speak a little bit louder so the microphone is sounds good. Okay. So we are welcoming today Syed. Yes, sorry. Okay. From Oxford. So yours.
Thank you. And thank you guys for inviting me. I'm looking forward to presenting. So I'm going to be giving you guys a talk today on how to do scalable inference using annealing algorithms. I do not expect you guys to know what these words are. So the fundamental problem that motivates this talk is we want to compute an expectation, right? So we have a complicated probability distribution. I'm going to denote pi1. We're going to assume it's very general. So like F is general, state space is general. And as you can imagine, this is not going to be analytically tractable in any problems that we actually want to use this. But we want to do these computations in. So one of the biggest methods that we often use is MCMC. It's the most popular technique. And the idea here is that we're going to solve this problem of exploring the state space by constructing a Markov chain that is going to explore the space, and we're going to eventually with the right statistics of our target distribution. And by averaging out across the trajectory, we effectively can invoke an ergodic theorem and do like a law of large numbers, and we recover our expectation. That's a story we tell ourselves, but the reality is often very different, right? So it looks like we had converged beforehand, but we'd actually turned out to have missed an entire different region of our state space. And a priori, we don't know what our target distribution looks like, because that's the point of running these methods. So it can trick us into believing that we have converged in cases that we have. And MCMC, one of the issues here is that this is a fundamental problem with MCMC with multimodal distributions. So when you have like local regions of high probability, so imagine I have a region of high probability over here, a region of high probability over there, but a value of low probability in the middle, I'm often going to get trapped in one area and never explore the other, even though in theory, and I will do it eventually, but in practice, I wouldn't. The problem becomes even more challenging when dealing with higher dimensions, constrained topologies, weird state spaces. In the context of, say, Bayesian inference, different modes of a posterior can correspond to, say, different plausible explanations for your data. And I want to make an argument. Actually, I'm going to hide this. So I want to make an argument that the fundamental issue with MCMC is the fact that it's a serial algorithm by construction, right? Like the way that I construct an MCMC algorithm is I tell you where to go next based off where I currently am. So I have to do one step at a time to figure out how to actually run the entire algorithm. And this has two issues, right? Because in their modern hardware has not actually the advancements in computation have not come from increasing clock speeds. The computer that you have now isn't that much faster than the computer you had about a decade ago. But what you do have now is way more computers than this. So modern computing is parallelized, and MCMC methods were not really designed or have a very hard time scaling up to parallelism. And there's another issue with not necessarily in terms of hardware, but in terms of the actual algorithmic performance itself. Like MCMC is, in order for it to explore the space, we're asking basically to do too much. Right? We have to both require to explore the space effectively, but also exploit the regions that are actually of high probability. And in practice, these are somewhat orthogonal tasks, and you end up failing at both. So what we can do is instead of running one chain, we can take advantage of the fact that we live in a world where parallel computing has become cheap. So we delegate the task of exploration to a reference distribution. So we bring so maybe a Gaussian or prior, something simple that we can do inference on, where exploration is easy. And then we're going to use our intermediary distributions. We're going to use our remaining threads to target different distributions that are there to assist the communication from the reference to the target. So by delegating the task of exploration to the reference and the task of exploitation to the target chain, we effectively have a mechanism of hopefully improving our inference. So this idea that I just described is called annealing. You guys may have heard of it, or in other words, tempering in the context of physics, but I want to move away from how we traditionally think about in terms of temperature, whereas I have a target distribution, which I'm going to note pi1. That's my hard distribution that's intractable. Think of posterior in your head. Then I have pi naught, which is my prior, which is something simple, easy, I can sample from, think of Gaussian. And then I'm going to have an interpolating distribution pi beta, where it goes from one to the other. And so I had a GIF here to show you it actually deforming, but I don't think it shows up in the PDF. But essentially, there are many ways of doing this. One canonical way that people often pick is what I call the linear path, where you're linearly interpolating between the log densities of your reference and target. But you can pick any other path, as long as the continuous interpolation, that's what matters. But you can already kind of see why this works, right? So if I have my complicated distribution in whatever space I'm working in, I've effectively turned this into a unimodal problem in one dimension higher. So if I've, in this diagram, I have my target where if I take a cross section, this essentially as my bimodal distribution. And so at one endpoint, I have the target, one endpoint, I have the reference. And by essentially having this one additional dial to play around with I beta, I've effectively created a tunnel through the reference between the different modes. So this, you can already see why exploration ends up being very effective. And in practice, we don't actually have a continuous thing to work with. We have to discretize. So I'm going to denote the annealing schedule as a sequence of annealing parameters where one endpoint is 0, the other endpoint is 1. This is a partition of the interval 0, 1. And this would correspond to different cross sections. And you can kind of already see what the sequence of annealing distributions will look like. So you're slowly deforming from one distribution to the other. So annealing itself is not an algorithm. It is a platform to build algorithms on top of. It's a technique, but we now need to specify how do we exploit this technique. So parallel tempering is the algorithm that I want to talk to you guys today. If you haven't heard of it, wonderful. If you have, hopefully this is something different. So the issue, the philosophy around parallel tempering is that we're gonna, instead of solving one problem that motivated the discussion, we're gonna solve n problems. So we're gonna make our life a bit harder so that we can actually make it a bit easier. So it turns out actually so we're gonna create a new Markov chain that's on an expanded state space where it's n, the state space is now n times the dimension, where the nth component is gonna correspond to the nth interpolating distribution. So if I want to say recover my expectation that I wanted to compute in the beginning, remember this is the whole point. I can just look at the last state and just marginalize around that and just pretend those are my samples. So I still recover my expectations if I do it correctly. So how do we actually construct this chain? Well, there's a two-step procedure. So one iteration of parallel tempering corresponds to, well, I'm going to initialize at whatever my states are at a given time. So I've showed 2 here, but there's n of them. So the first thing I'm going to do is I'm going to do a local exploration move. This is going to correspond to an MCMC move, at every component, independently of each other. Up until this point, I haven't done anything useful, right? Because I've effectively, I haven't done any useful computation until there's some communication that happens. So what makes parallel tempering is the communication step. So the communication step is going to correspond to taking adjacent states and proposing swaps, basically. So notice how in the local exploration loop, like I had the state that was closer to the target, which is a bit peakier, it had a harder time making the traversal, whereas the one that's closer to the reference, a bit more wider, it had an easier time making the traversal. So if I'm proposing a swap, there's two things that can either happen. I can either reject, because I can't accept all the time, I have to do some correction. So there's a metropolis correction here. So if I reject, well, I haven't done anything. I just go back to my local exploration. I haven't lost any computation other than the fact that I had to maybe do a proposal. But if an acceptance does occur, well, notice how there's a potential for magic to happen, right? So in one iteration, you actually, when I started off with the left mode, it ended up at the right. That wasn't because you were good at exploring in your near your target. It was because you were good at exploring near your reference. So this idea is something you can extrapolate and to show go back to the original example that we had. So if you run like a single Markov chain, you end up getting something like that. But if you run parallel tempering correctly, these are the types of results you can get. So notice how you make the traversal reliably and often between the different ones. And just to show that this isn't some just like hand cherry pick like Gaussian example, this is actually like happens pretty consistently amongst all the applications that we have. So these are 4 different examples of very multimodal problems of various complexities and state spaces. And you see the same random stability of in PT versus in versus this traditional MCMC. Okay, so up until this point, hopefully I've at least motivated that parallel tempering is like a problem worth thinking about, or at least like if you can get it to work correctly, there is something useful that's actually happening. Now, I've hit a lot of details under the rug, right? So there's a lot of design choices that come into running parallel tempering. I mean, the first one being, well, how do I actually propose these swaps? I told you how to do one, but if I have n swaps simultaneously, like, how do I orchestrate them in a way that's actually effective? Turns out if you do them poorly, you can actually get worse results. So if I'm trying to communicate information from one point to the other, how I schedule that communication matters a lot. If I have, how do I actually pick the annealing parameters? So turns out, so to go back, I guess, to the first point, like the way that people traditionally did it was they close their eyes at random, pick 2 states, and propose a swap. And that's basically appealing to reversibility. What we mean by that is, at one state, at one iteration, if I'm moving information or state towards a target, the next iteration can also potentially go backwards, right? So if I have n states, so if I have n distributions, I'm effectively communicating from the reference and target through a random walk. So that takes O(n) squared iterations, which is not going to win against the n distributions you actually have. So you actually get worse results by adding too many chains. Because of this reversibility, the design choices that go into picking the rest of the problems becomes really hard. It becomes very fragile. So in particular, the state of the art beforehand was like you want to appeal to a 23% rule. So you effectively reject 77% of the samples just to try to like fight the random walk. How do you actually pick these schedules? Because of the fact that you can't pick too many chains before deterioration in performance. For the hard problems you actually want to do this in, becomes really challenging. In particular, stochastic optimization techniques were the state of the art beforehand, which anyone here who has ever implemented a stochastic optimization algorithm knows that it can be harder than the underlying problem that it's trying to tackle. Before we figure out how to do the schedule, until we figured that out, even talking about the other design choices weren't even on the radar. So for example, how do we pick a better path? That was basically always pick linear. That's like, we don't even have the schedule down, let alone how to figure out how to do path optimization. How do you pick a better reference? Well, it turns out the prior isn't always the right thing to do. So you can talk about variational inference ideas there as well. Also, this is the one that's been really the motivation for why I got into this as well. Is some problems are just hard, and some problems you just did a bad job of implementing, right? So how do you know if the implementation that I have, if I try parallel tempering and it sucks, is it because of me or is it because of my problem is just hard? I need more resources. So being able to identify this, actually building diagnostics for analyzing our output is the other thing that I want to talk about. So before answering some of these questions, I wanted to just talk about what does it mean to actually optimize parallel tempering, right? To figure out like what is the best of all these, we have to figure out what we mean by best. And I want to really like focus in on the communication. Because remember, the local exploration move is very problem specific. And in some sense, like PT is a meta algorithm. The input in is an MCMC algorithm plus parallel threads, and the output is a better MCMC algorithm. So the actual understand parallel tempering, we have to understand these swaps. So I want to basically maximize the communication that's actually happening from the reference to the target. So from these like random, basically these states, if I have n machines, I'm effectively permuting the states over from one iteration to the next across the different machines, do these swaps. So I want to essentially maximize the total number of samples that I started at the reference that actually made this way to the target. Because whenever that happens is when the samples are actually doing useful work. So it's equivalent to essentially maximizing the restart rate. So the percentage of samples that actually make its way from the reference. This is our objective for parallel tempering. So I also want to, like for many people, you think of maybe something like the ESS when it comes to MCMC. And I actually want to make an argument that is a good proxy measure. And in practice, it heavily correlates. Actually, next week, if not next week, like by the week after, we're going to have a preprint actually showcasing some of the geometric ergodicity properties of parallel tempering. So there's actually rigorous theory that's not just hand wavy.
Sorry.
Yeah.
What is the cost? What do you consider as cost?
Just the runtime. So here are like the number of. So essentially, like if I'm increasing the number of chains, right? So I am also like, yeah, if I'm increasing the number of chains, I'm also increasing the total computational cost.
Yes.
Right. So you want to like, so just talking about the ESS doesn't make sense. You have to like normalize it to like the actual compute
Yeah,
update.
it's the computing time.
Yeah. So again, before talking about the benefits of, or like the corrections to these, like the proposed methods that we're introducing for parallel tempering, I want to just go back to talk about like why parallel tempering didn't work very well beforehand. So if you ever tried parallel tempering before our work, you probably know that it was not a very fun algorithm to use. And the reason for this is the fact that because of this random walk behavior that you're using to communicate from the reference to the target, by adding more chains, you're actually turning more diffusive. So like notice how by increasing the number of chains, you're effectively getting more random walkie or like Brownian motioning. These are technical terms. So remember, in this case, like this corresponds to the trajectory of a single machine of how the states on that machine are changing. So there's n of these, like for every run of PT, there's n of these diagrams. And useful work is only happening when you have a state that goes from 0 to 1. So you basically want to count the total number of up processes. So you can do the math, and it turns out the total number of restarts, or the restart rate, the percentage of samples that actually make its way across, is given by this one, where this looks scary, but let's break it down, right? So you have two terms. So you have the first term over here, the 2n, is essentially the penalty that you're paying independent of your schedule and independent of your problem. It's just penalty of having too many chains. This is the influence of the random. The second term is the influence of the picking a bad schedule, right? So the Rn is the probability that a swap between chains n and n plus 1 is rejected, right? So if one of the rejection rates is close to 1, the entire restart rate becomes random. So first of all, regardless of your schedule, you are bounded above in performance by 1 over 2n. So if I have too many chains, I'm just going to get bad results. But if I have too few chains, then the rejection rates are going to be very high. And I'm also going to get bad results. So for the hard problems where I need to have a large number of chains to stabilize the rejection rates, I'm effectively doomed for failure. So for the hard problems that I want to use PT for, this is not going to work very well. the fact that I can't also run a lot of chains and stabilize the rejection rates also means that my algorithm's performance can be very sensitive to the number of distributions and how it communicates. That makes it very impractical and not scalable to GPUs. If I have 1,000 threads at my disposal, I can't actually use them. Again, the state of the art before this was maybe pick 10 and try to adaptively reduce over time. So the solution turned out to be in the computational chemistry literature in 2001 under a very different name. And it's a two-line algorithm change. It's called the deterministic even-odd swap, which I'm going to call non-reversible. So instead of closing my eyes and proposing two swaps at random, I'm going to deterministically alternate between odd swaps, even swaps, odd swaps, even swaps. What I mean by that is odd swaps are going to correspond to proposing swaps between chains n and n plus 1, where n is odd, followed by the even swaps, which are going to be swaps between chains n and n plus 1, where n is even. So notice how, because I'm deterministically alternating between the two, I'm never going to propose the same swap twice. So that means in one iteration, I can never go backwards. I might have, if I can't go backwards, but I may have to wait 2 steps. And the fact that I can't go backwards, that means look, odd, even, you start to see the trajectories. Because I am only proposing swaps in the same direction if an acceptance occurs, I am effectively imputing in a momentum in every trajectory. So again, it's a two-line algorithmic change, but I effectively have completely gotten rid of the random walk. And instead of these zigzaggy lines, you end up getting, instead of getting these jaggedy lines, you get these straight line trajectories and converging. So this has some pretty dramatic impact in the performance. So if you compute the round trip rates, or the restart rates, sorry, there's a similar formula you get for the non-reversible variant. And notice how it looks very similar to the previous one, right? So instead of the only difference is the fact that instead of a 2n, we have a 2 now. But that one letter makes the entire world of difference, because if I now increase the number of chains, I don't pay a penalty anymore. So that means I can crank up the number of chains and I'm not going to get worse results. So first of all, non-reversible parallel tempering non-asymptotically dominates reversible parallel tempering, even though it's a two-line algorithmic change. So there's no reason you should ever use reversible PT. But also, as I increase the number of annealing distributions, as I increase, and as the distributions get closer and closer to each other, you actually get, the performance actually improves. There's a certain limiting number. So there's marginal gains when I add too many, but I'm not paying the same penalty of having, basically by adding too many, I'm missing out on, there's an opportunity cost and maybe I could have used the resource somewhere else. But whereas beforehand, the opportunity cost of my algorithm just fails. So we don't fail it. That lambda number, I'm going to come back to it later on. What I'm going to call the communication barrier. In some sense, it's an intrinsic number it's a number that intrinsically specifies the complexity of the difficulty of your problem. And also the fact that we don't get worse results by running too many chains. We actually get stability. So we can exploit that to design more robust tuning methods. And yeah, because again, it's also scalable now to GPUs, which we're also going to see that's a pretty powerful thing for our modern computation. Just to show you what the difference looks like, right? Is top is reversible, bottom is non-reversible. It's the only difference. You start to see how as I increase the number of chains, first of all, the top one becomes a bit more Brownian motioning, whereas the bottom one ends up just getting a bit more stabilized. If you look at the restarts in the beginning, this starts to increase, but then it decreases. Whereas with the non-reversible variant, you start to have a steady increase, but up to marginal gains. So I wanted to actually analyze the scaling limits and actually understand what's going on here. So if I take if I take these figures, right? So if I take the reversible trajectories, and if I speed up time by a factor of n squared, where n is the number of chains, and I keep the y-axis to always be between 0 and 1, you can ask what does these trajectories actually converge to? So it turns out for reversible PT, this converges to a Brownian motion, essentially, a reflected Brownian motion on the interval 0, 1. The details aren't really relevant. It's the fact that the scaling limit does not care about any of the design choices that mattered for my problem. right? So the fact that I don't see any influence of the reference, the target, the schedule, these are the things that I actually have control over. None of these things matter. The only thing that matters is the diffusion wins, right? So this means that you're not, all the things that you were, the tuning that you're trying to do for reversal PT is kind of pointless. However, for reversal PT, I can take the same figure, but instead of speeding up time by a factor of n squared, I speed up by a factor of n. Then you actually start to stabilize in performance, and you converge to not a Brownian motion, not a diffusion, but to a piecewise deterministic Markov process. If you know what they are, great. If you don't, it doesn't matter. But the thing is that it is different. So it's like at the heart of the system, non-reversal parallel tempering is fundamentally different than reversal parallel tempering. Also, basically these trajectories, what they look like is I go in a straight line with some rate lambda. I change my direction. I keep going in a straight line, and so on and so forth. So essentially, this lambda is that number that I was talking about earlier, is that communication barrier. And so you can see that as the increase in number of chains, you not only stabilize in your performance, but you also so you not only stabilize, but you see the influence of the actual design choices that you had through the communication barrier. So what is this communication barrier? I want to just talk about a little bit the geometry of the space of probability distributions. Whereas if I have like remember, the communication occurs through the rejections essentially. So I want to minimize that. So what is actually happening with the rejections? So it turns out the rejections are a proxy, or they're actually extremely related to the total variations. So if I have the two distributions right next to each other, when their overlap is really large, the rejection rate is going to be close to 0. When the overlap is really far, or there's very little overlap, then the rejection rate is going to be close to 1. So essentially, we can, by studying how the incremental change in overlap occurs, you can use that to define so by the score function is the Fisher score is measuring how the density changes with an incremental change in your parameter. So if I have my path and I change my annealing distribution by a tiny bit, it's measuring essentially how the mass has changed. So by looking at how the rejection rate changes as I change the mass by a little bit, I effectively can talk about the derivative of the rejection rate, and I end up getting this little lambda, which I'm going to call the local communication barrier, or the local change. And this capital lambda that I had earlier is the integral of that. So it essentially is measuring the cumulative change, or the cumulative rejection rate along my path. And a way you can actually interpret this is that this little lambda, so the score function defined essentially a velocity in my space of probability distribution is telling me where the mass is changing as a function of beta. This little lambda is essentially telling me my speed. It's essentially telling me what's the size of my velocity. And integrating the speed, I effectively get my length. So lambda, in some sense, you can interpret as the length of my path of distributions. So the linear path, so now this also gives us a mechanism of talking about optimization in terms of geodesics and the geometry of the space of probability distributions, right? So different paths now correspond to different algorithms, and different, so the optimal algorithm corresponds to the one with the lowest path. So you can actually show that the linear path turns out to be very suboptimal in most cases, but it's a good place to start off with. But the optimal path is one that's trying to both simultaneously maximize the overlap while also moving the mass. So this is what a geodesic looks like for two Gaussians with different, or two reference and target when the mass is very different from each other, and whereas the linear path is different. In the case of the linear versus optimized, you can actually show that the length of the optimized path is exponentially smaller than the linear path when the modes are, as the modes gets further apart. So you actually get an exponential gain in performance by picking a better. But for a fixed path, let's start asking, okay, what happens if I increase these are abstract numbers so far, right? So that's actually make them a bit more concrete. So by if I have a large number of distributions, you can actually show by summing up the rejection rates, which is diagnostic that I'm keeping track of anyway. It's cheap. I actually get an approximation of the interval. So the rejection rate is an approximation of the speed, essentially, of my curve from one point to the next. So by summing up the rejection rates, I actually get an estimate of my length. So by just running PT, I get a really cheap approximation for my length. And I can remember my objective was to minimize or maximize the restart rate. So this is, I can pretend this approximately equal to, right? And then I can just do this as a constraint optimization problem. And the optimal schedule turns out to be the one that is ensuring that the length from one distribution to the next is about the same. So this, another way of interpreting is we want to pick the schedule such that we are basically moving at a constant speed along the curve. And the rejection rate is approximately equal to the length divided by the number of chains of counts. So this is what it kind of looks like for an easing model, like so where you have like weird things kind of happen in between. So if there's like rapid changes that are occurring. So lambda is measuring the sensitivity to my annealing path for small change in beta. So like when there's a phase transition or like some critical behavior that's occurring, what you're essentially saying is that we want to impose more resources in areas where rapid changes are occurring, and we want to be, we can be a bit more looser in cases where things are more stable. So how do I actually learn this? Well, I run PT, I gain an estimate of my rejection rate, then I can do a cumulative sum and get like a spline interpolation essentially of my cumulative length. Then it's a one-dimensional inverse transform, and it gives me a better like schedule. So I'm effectively finding the unit speed reparameterization. And then I input that back into PT and I run it maybe like twice as long. And then I get better results. And then like I get a better estimate of the rejection rate. I keep iterating until I've depleted my budget. So every round I do the cycle, let's go round. So as you see, like as you increase the number of rounds, each round is a computational cost of all the previous rounds before. This has some nice benefits for avoiding some of the pathologies that come from adaptive tuning as well. But you start to see it starts to converge pretty rapidly, and over time, like as you increase the number of rounds, essentially like the optimal schedule is one that the rejection rates are all the same, right? So as you see, as you increase the number of rounds, that the rejection rate starts to decrease, or the variance of the rejection rate starts to decrease. The sum is always going to be roughly the same, so that's why the mean doesn't really change very much. So you can actually use this as a diagnostic plot to identify when you converge. And we just showed what the local communication barrier looks like as like a byproduct of the operator. So we benchmarked this against 16 different models in our JRSSB paper, and we ranging from baby toy easing models to 192,000 dimensional like phylogenetic inference problem on like cancer data. So these are not like baby toy problems. These are actually like scalable and useful. And these are what the diagnostic plots look like in all of these different cases. So we don't really have to cherry pick. This is surprisingly, shockingly stable. This is also what the local communication barrier looks like for different, like this is what the speed trajectories look like for different problems. And you notice how it's very rarely uniform, even for like various stats models, because weird complexities arise in a way that you can't really predict sometimes. And we don't need to, we don't need to figure out this, we learn what these are, right? Like this comes as a byproduct. We also benchmark this against other state-of-the-art algorithms, such as annealed importance sampling and SMC samplers. And we find that it's actually comparable to the state-of-the-art in the SMC world. This is an example in like the physics literature where it's called nested sampling. So this was a package called Dynasty. It's just like, this is the go-to thing in the astronomy world. So this was actually a plot that one of my collaborators was using for a very long time. Again, big design choices, a lot of money was spent because of this figure. After running parallel tempering, these are the complexities that we have. Notice how there are some cases like over here and here where like things are actually unimodal, and PT identified those. But in the cases where like Dynasty or nested sampling, it just, I think you have to pick an Occam's razor argument, right? Like we really assume that everything is unimodal, or maybe just the inference algorithm maybe performed suboptimally. So we also find in general about an order of magnitude improvement, essentially from picking a better schedule, and then another order of magnitude improvement by picking the non-reversible communication. So in most problems that we see, yeah, so this is an example of a posterior predictive, like where we were able to identify it's like slivers, and this is like a 30-dimensional like phylogenetic problem. And yeah, in practice, we end up seeing about 10 to 100x performance gain in ESS per second compared to state-of-the-art PT methods on a variety of complicated problems. So this is also not just toy things that I have worked on in my own work. These are for the last couple of years where this has been on the archive, or this has been out in the wild. This has actually been used by a fair number of large-scale projects in various research groups around the world. So some notable examples have been in the cancer world, where they use our work to model evolutionary dynamics of single-cell cancer genomes. There's like I think multiple Nature papers. In epidemiology, a couple of months ago, they used some scientists at Berkeley used our work to identify genetic variations in malaria. My favorite one is in political science. And 2 years ago, I guess they used our work. Some people at Georgia Tech used our work to identify gerrymandering in Georgia's 2021 congressional district. I think one of the biggest impacts of this work, again, because PT is not an algorithm itself, it's a meta algorithm. It's an inference engine for other algorithms that you have for your specific problem. So it's a very powerful tool for a probabilistic programming language. So there's been quite a few languages that have already implemented our work as kind of the engine that runs it in the background. The biggest application of our work has been with the Event Horizon Telescope. So the Event Horizon Telescope was a collaboration of a couple hundred scientists around the world, where they like synchronized the Earth to turn. They basically had like 5 different telescopes, eight different telescopes around the world, where they synchronized to turn the Earth into a lens to capture the light that turned into the first image of a black hole in 2019. So this was actually done before our work, but once you like take into account all the math and physics and the engineering, at the end of the day, you have a bunch of sparse, noisy, temporally correlated data, and you want to infer an image. So this is a Bayesian inference problem, and in the background, they're using parallel tempering before our work. So in 2021, they implemented our work, and they were able to recreate the results of the original photograph in about 2% of the computational budget. So these are diagnostic plots in Paul Tita's PhD thesis. He was in the implementation. So just to show that our diagnostics are actually like usable by other people as well. So you can see from his thesis as well, like the influence of PT versus the state-of-the-art methods that they had before. So the y-axis is the log likelihood, higher is better. The x-axis is the computational runtime. The green represents reversible parallel tempering with this MCMC method they had called the differential evolution in the physics literature. The burgundy here represents like what happens when you take the same MCMC algorithm as the Explorer, but just use non-reversible PT, you get like a better performance. But when you also have a better local move, so here like the blue and the orange represent when they use HMC and slice sampling respectively on top of non-reversible PT, and they're basically able to get like this dramatic shift. The gray is the 10-day long average. So these are some of the design choices that actually led to the discovery of so these are some of the computational advancements that led them to tackle new problems they weren't able to because of computational limitations. Notably, in 2021, they discovered magnetic polarization using our method. This was this picture with the swirls in M87's photo. And then I guess 2 years or a year and a half ago, they used our work to discover or generate the first image of Sagittarius A star, which is the black hole at the center of our galaxy. So since then, there's been a lot of work that I can talk about. In particular, we've done basically this talk so far has been on the first paper, which was on just how do you do better schedule tuning and how do you make parallel tempering scalable and how do you optimize the schedule. Since then, we've also identified how to do path tuning. How do we optimize the reference, incorporating variational inference into your pipeline? We've also been able to design local explorers that have gradients that adaptively tune synergistic with PT. This was a paper that came out, that just got accepted to ASDAPS. Our work has also been implemented in an open source scalable implementation in a package called Julia, pigeons.jl in Julia, which the paper for that is currently in review. And yeah, we also, again, 2 weeks from now, you'll see a paper on the geometric ergodicity properties of PT to actually show this is when you start to see all the restarts actually occurring across all the chains, it's actually a really good sign of burn-in has actually occurred. And so you can use the restarts as a proxy measure of the actual effective samples that you're trying to make. So how much time do I have left?
5 to 6 minutes.
Okay. I want to give a very high level overview. I'm gonna skip a couple of things, but the first thing that I really wanted to really talk about was I've talked about parallel tempering does a good job, and it's like it does a surprisingly good job, almost too surprising. And there's other algorithms as well that I could also use. Why should I use parallel tempering at all? And also, like, why does annealing work at all? Right? Because parallel tempering is a special case of parallel tempering is just metropolis Hastings. Like an independent metropolis. If I get rid of all the annealing distributions, then I just recover independent metropolis Hastings, which we all know it doesn't work very well. And also you have these other algorithms like annealed inference sampling, sequential Monte Carlo samplers, like that also perform very well when tuned correctly. So when should I use one versus the other? So this has been the question that I wanted to answer. So in particular, like we see like a big difference. So like all the work that I've done so far has been showing like in the case where n goes to infinity, where the number of distributions becomes very dense. Whereas the case where things are sparse, things become very fragile. That was the reversal PT scenario. In practice, is there some like limiting point where in the middle where things are, they start to be good, but not fragile, but also like perform well enough? So I am not going to have time to talk about all of this stuff, but I want to. So there is this other sister algorithm called sequential Monte Carlo samplers that I just want to like really touch base on. So instead of, it works similar to parallel tempering, but instead of building the distributions one at a time, or by building the path simultaneously, build the path one at a time. So if I have a bunch of particles that start off approximating my distribution at a time t, then I can effectively generate this set of approximations for the next distribution by doing the same local exploration loop, but applying it to each particle one at a time. So here I started off with some particle approximation, then I nudge each of them towards their respective next target distribution. And then I'm going to do importance sampling to reweight. So like instead of using metropolis Hastings and parallel tempering, we're using importance sampling as a correction factor. And then we're going to do a resampling operation, which is essentially going to repopulate like the weights that are higher, and we're going to kill off the weights that are small. So essentially, like at one iteration, you start off like over here in the next iteration by doing this same local exploration communication loop, you end up getting a next particle approximation for your next distribution. I don't want to spend too much time on the details here, but essentially, like this is what the picture looks like, right? So parallel tempering, initially, I start off with like one state at every distribution. Whereas with SMC samplers, I effectively have all of the states of the reference. The next time step, after doing it for a bit longer, PT is simultaneously repopulating the entire path a little bit at a time. Whereas SMC samplers is building the next distribution one at a time. But if I if I have n distributions, or if I have the same number of annealing distributions, and I run it for t units of time, this is the result that I get. I get a particle approximation for all my path, just constructed in a different way. So in some sense, like the parallel tempering and sequential Monte Carlo samplers, whichever, again, whenever you can use one, you can use the other. They are doing the same thing, but they're swapping the role of memory and time. Again, if you've seen this before, great. If you haven't, like, just run with me for this a little bit. So in again, like, so in some sense, parallel tempering is actually not a parallel algorithm. Remember, it's a serial algorithm because if I want to generate twice as many particles in each of the states, I have to run it twice as long. Whereas if I want to, for a sequential Monte Carlo, if I want to generate more particles at the target, I have to initialize and have double the number of particles simultaneously that I'm simulating, right? So like here the particles are generated or evolving in parallel, whereas here they're populated in sequential. So the role of annealing and parallel tempering is adding a parallel cost to essentially stabilize a serial algorithm. And the role of annealing in sequential Monte Carlo is adding a temporal cost to stabilize a distributed algorithm. So in both cases, I can construct an estimator for the normalizing constant and the expectation, right? So in parallel tempering, I can take my last distribution, my last particle approximation, and then that gives me an unbiased or a consistent estimator for my expectation. And then the sequential Monte Carlo, I get a consistent estimator by increasing the number of particles. So here, remember, n is always our parallel cost, t is our temporal cost. So you're kind of trading off between the two. We also get a normalizing constant estimator for both. Right, so and look that they look scary, but the only difference is that I basically get one from the other by swapping the n and the t. So the same like functional form exists for both. So you can start asking, like, given these, like, how much resources do I actually need to invest to get a stable estimate? I just want to, I'll be another 3-4 minutes and then I'll. So how many resources do I need to spend? So I like to get a stable variance estimate with using the same number of annealing distributions. For parallel tempering, how long do I need to run it for? And for SMC, how many particles do I need to get a stable estimate? So the way that I can study this, again, this like that lambda number that I was talking about earlier, which represents the length of my problem, i.e. the difficulty of my problem. I want to, intuitively, we want to increase the resources proportional to the length, to the difficulty of our problem, right? So in the case of parallel tempering, that means that I'm going to increase the number of distributions proportional to the length. So that's the number of parallel threads that I'm running. Whereas in sequential Monte Carlo, that's going to correspond to, again, the number of annealing distributions is my runtime. That's going to correspond to the total number of, the total time I turn my algorithm for. So if I have the case where the number of distributions is sparse relative to the length of my problem, right? So if the number of distributions grows smaller or slower than how quickly my problem grows, then you need an exponential number of particles, essentially, to get stable variance. So in the case of parallel tempering, you need exponential runtime to get variance of your normalizing constant estimator down to epsilon. And in the case of SMC samplers, you need an exponential number of particles. In the case where alpha is equal to 1, so where the number of distributions scales similarly to the length of my problem, then you actually go from exponential to linear. So instead of needing an exponential runtime, I need like a linear runtime in parallel tempering. And instead of needing an exponential number of threads, I need a linear number of threads in the difficulty of my problem. And in the case it's dense, where I have a lot of chains in between. Notice how here I have no overlap, whereas here I have a lot of overlap. Again, the communication occurs with the overlap. So when I have a lot of overlap, if I have a sufficient amount of overlap, where the overlap grows faster than the difficulty of my problem, then I actually need a constant runtime, and uniformly in the entire set of all problems, essentially. So this critical transition from exponential to sublinear indicates that there is a critical phenomenon that occurs with annealing, not just for PT, but for annealing algorithms more broadly. And I did this very special, I'm here presenting in a very special case of SMC samplers, but like this actually generalizes to annealed importance sampling and general SMC samplers in with different forward and backward kernels that can work with. And you can also see like the actual normalizing constant estimator as like a function of the total number of exploration evaluations. And you basically get the same thing for every problem that we tried. So these are for different PT algorithms with different number of chains, as well as SMC samplers and AIS. So in particular, like in the punchline, so when should I use PT versus SMC? It turns out you should use parallel tempering when you are not poor in memory and rich in time, right? Because we want to increase it, you want to run it as long as possible, but you only need a certain amount of chains. For SMC samplers and AIS, you essentially want to be not poor in time, but rich in memory. And if you are rich in both, turns out the scaling is exactly the same. And if you are poor in both, you're screwed. So that's essentially the punchline. So like, it's not like one is better than the other. It depends on what your algorithmic constraints are and what your computational constraints are. So in summary, non-reversible parallel tempering, if you got anything from this talk, is better than reversible parallel tempering. And if you have tried PT in the past, and it's probably worth trying again if you probably did. We've identified why this occurs using the scaling limits of PT. We optimize this optimal schedule using the output of PT itself. We've developed natural efficiency metrics useful for practitioners. Our analysis also makes no structural assumptions on the state space or the target. And we also have developed guidelines for both path and reference tuning, as well as an efficient black box algorithm within implementation. And finally, we have identified why annealing works more generally, not just for PT. Thank you.
You for the talk. Unfortunately, we've run out of time. There are some people waiting outside, so I invite you to keep the discussion upstairs. And just to remind you that next week we are not going to have a seminar, so we will be again back in. Thank you again. The next one.